All right, let's get started on this. Let's talk about 1.5, transformation of functions, perhaps the single most important thing that we talk about all year. So let's begin, as always, with a definition of the general form of a function. So the general form of a function, f of x, is, for some a, b, c, and d in the real numbers, capital G of x equals a times f of bx minus c plus d. Now, each one of these different functions. So the general form of a function, f of x, is, for a, b, c, and d, some real numbers, g of x, we like to use a capital G to denote the general form of a function, that's just a me thing, is a times f of bx minus c plus d. And each of these variables, a, b, c, and d, again, just some real numbers, each have different effects on things. First, I want to talk about c and d, because they're perhaps the easiest of our transformations, and then we'll move on from there. So c and d handle translations. If d is positive, that is this guy out here, if d is positive, then your function f, your original function, is shifted up d units. If d is negative, your f is shifted down d units. I'm going to go ahead and define c here. So if c is positive, f is shifted left c units, and if c is negative, f is shifted right c units. So I'm going to pull up Desmos here real quick and go over this with you. So if you look for a moment here, you'll see that I have plotted x squared such that the input was bx minus c, and the a and the d were all on here exactly the same. And we'll go over this more in just a second, but for now, understand that I've set up some sliders here, and as I slide these sliders, you can notice what happens. So right now, a is 1 and b is 1, and we'll leave them like that for now. And you'll see that what we've actually graphed is just x squared. This is just x squared. We're not subtracting anything from it on the inside. We're multiplying it by 1, both on the input and on the output, and we are adding to it exactly nothing. So this is exactly x squared. But watch what happens when I take and drag over the d value here. You can see as it increases. And it's just shifting up. And as I drag it back down, it'll continue downward. And you can see that the d value here, as it becomes more negative, it just pulls the whole thing down. And it increases the entire graph as it comes back up. And that's perhaps the easiest way to see it. I'm going to reset this back to 0. And that has about the same behavior you would think. So adding to the output, that is outside of the parentheses, adding to the output does exactly what you would think it would do in terms of increasing. But you may notice that as I actually increase your c value, watch what happens to the... watch what happens to this. It does go right, like it should, and it goes left, like it should, just like you would think. Now, you may be sitting there thinking, well, okay, that behaves exactly why. What's so weird about that? Well, notice that we used a minus here in the general form, and we did use a minus in the general form, and on purpose we used a minus so that everything would work like it did. But look, if I use a plus instead, let's say that we decided to use a plus instead, that would mean that our c, look, as I move this further to the right, this is kind of trippy, the graph itself is shifted to the left, and the same thing as you make it more negative, it's shifted to the right. And that is a strange behavior. So in general, we like to just go ahead and call this a minus. But do remember that when you are in effect adding to a input value, you are shifting it to the right. And when you are subtracting, and do remember that when you are adding an input value, you are shifting to the left here, and when you are subtracting an input value, you are switching to going to the right. Look here. I am increasing the value by which we are subtracting. I am subtracting c. As I increase the value by which we subtract, I am moving to the right. That is the thing to keep in mind. Basically, everything inside the parentheses works opposite of how you would think. This is pretty plain again. If you change this back to plus, adding more moves to the left, subtracting more moves to the right. It's strange behavior, yes, but it has to do with how we move our inputs around. So let me change this back real quick. And we'll come back to this in just a second when we need to look at what A and B do. But overall, try and remember, if D is positive, we go up. If D is negative, we go down. If C is positive, that is inside of the parentheses, we shift left. If C is negative, we shift right. So if A is negative, the function is flipped over the line y equals D. And if B is negative, the function is flipped over the y-axis. We call these reflections, whereas we called the previous action of just shifting it around on the graph a translation. So you have the three different types of reflections, translations, and dilations. You may remember that from geometry, and we'll write down all three of them in just a second when we've talked about dilations. But I want to talk about reflections here using Desmos. So I've changed this real quick to be a little toggle switch, and you'll notice that when we switch this from being a positive A to a negative A, it flips it over, well, it looks like it's flipping it over just the x-axis, right? And you could say that in this case, but what I said was that this flipped it over the line y equals D, which I'm going to go ahead and make, let's say, green here and dotted so you can see it a little bit better. So as I actually raise D up and raise the entire graph up, therefore, you can see that as I flip this, it's actually just flipping it over that line. If you were actually flipping this thing over the y-axis, over the x-axis rather, which you can totally do just by making the entire function negative, that is negative g of x, it would flip from here all the way down to -2, and the parabola would have its vertex there instead. So remember that changing A to be negative is going to flip it over the line y equals D, that is however far up you've moved it. And then let's move this back down for just a second to 0, and we can turn this part of the layer off. And then I say that switching this over to -1, that is flipping the B from positive to negative, is going to flip it over the x-axis. So let's look at that. Wait a second. Oh no, nothing happens, you say. Well, you take a second to think about why nothing would happen here. Why isn't it showing this? It says that it's supposed to flip over the y-axis. Why isn't that working? Well, it should become pretty obvious once we've shifted C over just a little bit, perhaps, what's happening once now we're able to do it. Oh, okay. So now it's going to flip over just like it should. So you take a second and think about why, when it was at C equals 0 here, it was focused over the y-axis, what was happening. And you should be able to figure out that it was flipping. It was just sending everything that was defined over on the right-hand side to the left-hand side. But since this is a perfectly symmetrical function, you can see that it was just mirroring it onto itself. If I were to change this, for example, to the cube function, which looks like this, you can see very clearly that moving it around shifts the cube function exactly the same way. But also, it's going to mirror in a way that we can see a little bit better. By the way, just because this is a cube function that's been transformed, let's say we want to move it up a little bit, and we want to move it to the right a little bit by subtracting 1, and we want to flip it like that, it's going to have the exact same, it's going to be behaved and be moved the exact same way as the squared function. It's going to be moved exactly the same way as your first degree function that's a linear function. It's going to be moved the exact same way as an absolute value function, or a square root function, or a logarithm, or an exponential, or any of the things that we talk about in these classes, guys. They all move exactly the same way. So no matter what your function is, they're all going to be moved, translated, reflected, and dilated exactly the same way. So I want to talk about dilations for a moment. I want to write out the different definitions and things that you need to know about what dilations, reflections, and translations are, collectively called transformations. I want to make sure that we know that. And then I want to show you how to actually put these things into a general form and how to think about graphing them by hand should you need to. All right, so if a is greater than 1, the graph of f is going to be stretched. If a is between 0 and 1, that is, if a is a fraction, the graph of f is going to be compressed. B works exactly opposite. So if your a is a whole number that's bigger than 1, any real number bigger than 1, really, your graph is going to be stretched. If it is a fraction, it'll be compressed. For B, it's the opposite. If it's bigger than 1, it's going to be compressed. If it's between 0 and 1, it's going to be stretched. Now, importantly, you need to think about what is, which one is horizontal and which one is vertical. And there's an easy way to remember it. If we look one more time at, let's do it in yellow here. If we look one more time at the general form of a function, which I'll write out again. So it's g of x equals a times whatever your function is, evaluated at bx minus c, and then we're going to add d to it. Okay. The easy way to remember this, whether it handles horizontal or vertical stuff, is everything in the input handles the horizontal stuff. So B and C each handle horizontal things, and A and D, let me do this in a teal here, A and D both handle things in a vertical or up and down sense. So A and D are going to handle vertical stretches, because A is going to handle stretches. D handles vertical shifts. A handles vertical stretches. B handles horizontal stretches and compressions. C handles horizontal, because it's on the inside, shifts. C and D handle your shifts, your translations. A and B handle your reflections. That's just based on what the sign is, and they're also going to handle your stretches and compressions. And I know that this is a lot to just throw on you all of a sudden. So let's take a look at this. I've reset everything back to your a times b of x, b. So let's take a look at this. I've reset everything back to your squared function. That is, your f of x is x squared, and we've plugged bx minus c into it, put on the a, put on the d. We've got our general form here. So what I'm going to do is I want to look at what happens when you increase a, that is, your a is bigger than 1. Well, watch the graph over here as I increase a to be bigger than 1. It stretches it horizontally, and you can think about it just picking up here and just pulling up and stretching it taut, like you had nailed a piece of bungee cord into the floor and you're just standing up above it, pulling on both ends of it as it increases. And then I'm going to get it back down here to about 1 again, and you can watch as I make it more and more fractional, it compresses it and compresses it and compresses it, all the way to a line when it's 0, in fact. And then, of course, when it becomes negative, it has the exact same behavior. You can think about nailing it now to a ceiling and pulling down on it. As it gets bigger or more negative, it still gets stretched, except it's getting stretched and reflected because it's negative. All right? And you can think of it the exact same way for B, except it's going to be more compressed as it gets bigger, and it's going to be more stretched when it gets pulled out this way. Now, perhaps it's not quite so obvious for a function like this, so let's talk about the square root. Let's talk about the square root here. So we're going to do the 1/2. This is what the square root function looks like. So I'm going to stretch it vertically. You can see it's being pulled up. And then I'm going to compress it. You can see that it is being pushed down as it gets more and more negative towards 0. And then for B, it's going to get compressed horizontally. You can think about it being pushed from over on the right side up against the graph. And then as it gets to be more fractional, it is being stretched horizontally. Though, to be honest with you, the very best function for this is a function that you won't even see until trig. So don't worry too much about the definition of the sine function here. It's a very strange-looking function that we're going to do an entire class to talk about. But I want you guys to see that even with strange exotic functions that you've never seen before, as your a increases, the whole thing is stretched vertically. As your a gets closer to 0, it's going to be compressed. I'm going to put that back to 1 now. As your b gets larger, the entire thing is going to be like a spring compressed in. And this is in fact why it's called compression, is because of the behavior of this exact function. And as it becomes more close to 1, it is going to be stretched horizontally. Of course, you can guess what c is going to do. Since we have the minus in here, increasing this function is going to make c more negative. Therefore, it's going to be shifted to the right because it's becoming more negative. If we go to the left, it's becoming more positive. It's minus a negative, which is a positive. That's going to shift it to the left as expected. And then d, of course, is just going to pick it up and down, just like expected. So even bizarre functions that you've never seen before, and indeed you won't see again until trigonometry, have this exact same sort of behavior. So that, in short, is what all of this is. So I want to talk about the general form of an equation again, and sort of how to think about how to write this, and what I mean by the general form of an equation. So let's look one more time at a times whatever your original toolkit function, as we call it, was, f of bx minus c plus d. You have a few different kinds of things to think about here. So c and d are called your translations. Okay. Remember, if you make your a and your b negative, that has to do with reflections. And remember, depending on the value of a and b, they can do other things as well. They can deal with what's called your dilations. Okay, and each one of these have simpler meanings. These are just shifts. So being moved around on the graph. Reflections are being flipped, is another easier word for it. And dilations has to do with stretching and compressing, like a spring. So you've got your translations, your reflections, and your dilations, and maybe some simpler words for it. Collectively, all three of these things together are called, the title of a chapter, transformations. It is very common in the beginning when we start talking about these to talk about translations as transformations because they look kind of similar. They're not even close to the same thing, though. A transformation is any of these things. A translation in particular is just moving things around. So let's look at an example here. And indeed, it'll be the only example. And then I'll show you all a neat tool on Desmos that I'm going to link in the lesson materials at the tab at the top that you all can go play around with in Desmos yourself and see. And you'll see that there is a very easy way to think about how to transform these functions. And I'm also going to go ahead and link in the same exact tab below that a Desmos activity that you can do that I highly recommend that you do that will help you with this, where it will show you step by step how to walk through this. You're going to need a Desmos account. If you haven't already signed up for one of those, just go make you an account on Desmos.com using your school email, and you should have access to all of that, and I can see that you guys have done it and all that. It's not for any kind of extra credit, but if you want a good understanding of what's going on here, I have a good activity for that that you're totally going to be able to do. So let's look at this example. So the example here says, given f of x equals x squared and h of x equals the square root of x, it says write the transformation of each function, so both f of x and h of x, if they were both shifted right 3 units, down 2 units, flipped over the y-axis, and compressed vertically by 1/3. So we can actually do all of that in this space right here. So let's talk about f of x first. So f of x, if we have x squared here, its general form is going to look like a times, and then we're going to plug in bx minus c, and we're going to add d to it. So we're going to need to multiply out front by something, and the thing that we multiply out front by has to do with the two things here we can see in our little key here, reflections and dilations for a. So we know that for our g of x, perhaps for our f of x, this is just going to be, and I'm going to rewrite this again, this is going to be a, whatever a is, times f of bx minus c plus d. So this is just going to equal a times, and then what is f? Well, f is something squared. Well, what do we plug in? Instead of x, we're going to write, we plugged in bx minus c, so it's just going to be bx minus c. And then what did we do to the input? What does f do to our input, bx minus c? Well, it takes the x and it squares it. And then this said we're going to add d to the outside. So this is the function that we're working with, and we just need to know what all of these terms are. So once you've got this form written this way from the general form, we need to come over here and see what our values of a, b, c, and d are. Now, if we're going to be shifting to the right 3 units, we're going to need to shift to the right 3 units. We know that we're going to have to end up subtracting overall. So if we plug in c equals 3 to this general form, we will be subtracting 3. That's going to move us to the right. That's what we want. If we want to be shifting down, that is shifting, look here, shifting is a translation, and up and down has to do with the d value. So we know that our d is going to be, well, 2, because it's being shifted, and since we're doing it down, it's going to be negative, because that behaves like you think it would, because it's on the outside. We're going to need to flip over the y-axis, that is, that's a horizontal flip over the y-axis, like closing a book. So flipping things, look here, that's a reflection. Here's the reflection, B. So since we're going to be flipping it over the y-axis, our B is going to be, well, it's going to be negative. We know it's going to be negative, but we're not doing any dilations with B. It doesn't say anything about compressing or stretching horizontally, so that's just going to be -1, like I showed earlier. And then we're going to compress vertically by a factor of 1/3. That should pretty obviously make a 1/3. Since we're doing it vertical, and it is a compression, that is a compression, that's a dilation. Dilations are A and B. It's vertical, so it is A. Basically, this is just look up in your notes, read the definitions, figure out what's what. Now we're just going to fill in everything to this general form formula, and you're done. So this will be 1/3 times -1 minus, -1x rather, minus whatever c was, which was 3, squared plus whatever d was, which is -2. And then, of course, you are going to finish this up real quick. So this will be 1/3. We don't write -1 times x. We just write -x minus 3 on the inside, squared. And we don't write plus a -2. We just write -2. And this right here, you should be able to read this and say, okay, well, we took the square function as our normal function that we know that what it looks like. And we have multiplied it by negative in here, so we flipped it over the y-axis, because I know what that does. We've compressed it vertically by a factor of 1/3. We have shifted it to the right 3 units, because we're subtracting in here, and down 2 units as well. So I should be able to give you this, and you figure out what's going on as well. Now, let's look at f of x for just a moment, and I'm going to show you that we get this. If we look at h of x, you'll notice, watch this. If I just change this instead to an h of x, the only thing I would have to do is change all of these things to a square root. So let me show you really quickly what we get when we do that. In fact, I can just do it over here. I'll even do it in a nice green color here. So if we want to do this for h of x, we can consider a times h of bx minus c plus d as the general form, but this time we're going to use h of x, which is the square root of x. So this is just going to be a times the square root of, and we plug in bx minus c plus d over here. And of course we did the same thing to both of them. So since we did the same thing to both of them, you can see pretty clearly what we're doing with this is the exact same things, which means that the A, the B, the C, and the D all have the exact same values. So this will also just end up being 1/3 times the square root of negative 1x minus 3 plus a negative 2. So instead of squaring this weird input, we're taking the square root of it, and you're going to get 1/3 times the square root of negative x minus 3 minus 2. It is the exact same thing done to a different function. Everything behaves exactly the same way, and you can see that h of x is over here, and you can see that we did our f of x in this nice teal color here. I'm going to link those Desmos videos for you guys, the exercises rather, for you to play around with on the calculator that I've made, and then a really nice set of Desmos links for actually playing around with the stuff. If it isn't clear to you what's going on here, after one example and a few minutes of me talking and going over kind of what's going on here, that's okay. It's entirely expected. You're going to need to go play with that a bit. Look on Khan Academy, do some work with that, do some work in Delta Math. By the end of you actually playing around with this, you'll have some work with it. Like anything in mathematics, guys, this is a bunch of theory with an example, and genuinely, the best way to do this is just to play around and look at all the stuff. So look up in the Materials tab, go through some of the Desmos exercises, and see what you can do with those. In fact, I actually believe what I'm going to do is up in the Materials tab, I'm going to link the single Desmos calculator thing for you to play around with, and then I'm going to actually include all of the Desmos activities themselves as separate activities for you to mark as complete in subparts of this lesson. So that's how that's going to be done. But until the next time, I'll see you guys in class.